This is problem 1, and in this one we're asked about helium-3 and helium-4, and we're asked if they're fermions, which means that it's got a half integer spin, or bosons with an integer spin. So with helium-3, it consists of 1 neutron and 2 protons. So each of the neutrons and the protons has spin 1/2. So N has spin 1/2, P has spin 1/2. Now, when nuclei are feeling just the same as when atomic shells are spinning, the spins tend to cancel each other out wherever possible. So here we can have a spin plus 1/2 and the spin minus 1/2 proton. So the protons can sum together to give 0 spin, but that still leaves a neutron left over with a spin 1/2. So for helium-3 has spin 1/2, and so it's a fermion. Now with helium-4, we've got 2 neutrons and 2 protons. So the spins for the 2 neutrons can cancel out, and the spins for the 2 protons can cancel out. So in this case, helium-4 has spin 0, and if it's got spin 0, this tells us that it's a boson. Okay, so this is problem 2. In this one, we're told that an electron cannot decay into 2 neutrinos. So let's put 2 neutrinos there, and then we'll consider all the laws that this breaks. Okay, so energy, not necessarily. These could be very energetic neutrinos. It would be hard to get rid of all the mass energy of the electron this way, but technically it's not necessarily violated. Part B is spin. Now the neutrinos each have spin 1/2 and the electron has spin 1/2. So in this case we would be creating spin. So that's not possible. So B, spin, is violated. Charge. Now an electron has a negative charge and the neutrinos have no charge. So we're going from something which is charged to something which is not charged. So that is bad, that is violated. Okay, so let's consider lepton number. The lepton number of the electron's 1. The 2 neutrinos both have a lepton number of 1 as well. So we've gone from on the left-hand side having a lepton number of 1 to on the right-hand side having a lepton number of 2. So that again is violated. So lepton number violated. Linear momentum, it's possible that that could be conserved. Again, it would be hard because the electron's much heavier than the neutrinos, but it's possible. And baryon number, everything here has a baryon number of 0, so baryon number is conserved. Okay, this is problem 3. In this one, we have a pion decaying into a muon. That's actually an anti-muon because that's positive. And some type of neutrino. Now a pion consists of an up-down quark. And in the first part we're asked to classify each particle as a fermion or a boson. So fermions have half integer spin. So in the above example, the muon and neutrinos are fermions, and then we've got bosons, which is an integer spin, and the pion has 0 spin, so the pion is a boson. And then we're asked, are they leptons or hadrons? So leptons are electrons, muons, and tauons. So the muon and the neutrino is a type of lepton. So these are not composed of quarks. Hadrons, on the other hand, are comprised of quarks. And so we said this pi was composed of an up and an anti-down quark. So it is a hadron. Okay, part B then says, what is the type of neutrino created in this decay? Okay, so here we have an anti-muon. So we create not an anti-neutrino, a proper neutrino. And so this is going to be a muon neutrino, so that the muon lepton number is conserved. Whenever we create a muon, we create an anti-muon neutrino. If we create an anti-muon, we create a muon neutrino. Okay, part C, write down the equation for the decay of a negatively charged pion. So in this case, we have a negative pion. It's going to, this is the antiparticle of this one, so we're going to get the antiparticles. So we get a muon created, and if we're creating a muon, we create an anti, that should be muon neutrino. Okay, this is problem 4, and we're told that a neutral pion decays into 2 photons, so gamma plus gamma, and the rest mass of the pion is equal to 134.976, and that's mega electron volts on C squared. So we know that E is equal to mc squared, and so this is an energy divided by c squared to get the mass. And we're asked to calculate the wavelength of the photons, and we're also asked why must they have the same wavelength. So why are we creating 2 gamma photons here with the same wavelength? Okay, now let's answer that first. That comes down to momentum conservation. So on the left-hand side, this is a pion at rest, so it has no momentum. So on the right-hand side, we can have no momentum as well. But photons are forced to move. They must travel at the speed of light. So, and photons do have momentum. The momentum is given by E on C. And so we need to create 2 of them traveling in opposite directions so that their momentums can cancel out, and so that we can have 0 momentum. So they must have the same energy but be traveling in opposite direction. So the photons must have same energy and hence wavelength, but be traveling in opposite directions. If we only had 1 photon created, there's no way that we could have 0 momentum. So in this case, momentum would not be conserved. Okay, and now we need to calculate the wavelength of these photons. So we know that the energy of a photon is given by hf. Now this is the mass of the pion, so the energy of the pion is equal to this times c squared, so the energy is equal to 134.976 mega electron volts. Okay, and there's 2 photons created, both with the same energy. So the energy of the pion is equal to the 2 times hf, where f is the frequency of each of these photons, and the factor of 2 just comes because there's the 2 photons there. So this is equal to 2h, and then f is equal to c on lambda. And so we can rearrange this. We have lambda is equal to 2hc on E, and so this is equal to 2 times 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over E, which is equal to 134.976 times 10 to the 6, because we've got a mega there, and then times E, the charge on an electron, to get it into joules, 1.602 times 10 to the minus 19. And now solving that, we get 1.84 times 10 to the minus 14 meters. So that's the wavelength of the photons. Okay, this is problem 5. We're told that a proton comprises of 2 up and 1 down. So we've got up, up, down. And we're asked in part A, if the down quark is blue, what are the colors of the 2 up quarks? Okay, so the combination must be colorless. So since we've got 3 quarks, we need to have a red, a green, and a blue. So the up quarks must be red and green. Okay, part B now says a neutron comprises of 2 downs and 1 up. So we've got down, down, up. And explicitly describe in terms of quarks how the above proton could be transformed into a neutron. Okay, so in terms of quarks, we need to get from an up quark to a down quark. What would be the color of the quarks in the neutron created in this process? Okay, so if we wanted to get from an up quark to a down quark, we could do that by absorbing a pi minus meson. So a pi minus meson consists of an anti-up and a down quark. So if this proton absorbed the pi minus meson, it would convert into the down, down, up. And now the question's asking what are the colors of the quarks. Okay, so if this up quark's this one and it's still red, say, so that can be red. We already had a down quark which was blue. So we must now be replacing the green up quark with the green down quark. So for our meson that we're absorbing, this is going to be a green down quark and an anti-green up quark. So the pi minus meson is also colorless. So this is problem 6. We're told that we can estimate the range of the strong force by considering the creation of virtual particles where the uncertainty in the energy is given by mc squared. And they can exist for a lifetime delta t. And from the uncertainty principle, we know that delta E delta t is greater than or equal to h bar on 2. And the furthest that a particle can travel in its lifetime, delta t, is given by c delta t. So we're asked to use this to find range of strong nuclear force which it can do by exchanging neutral pions. So the mass of the neutral pion is equal to 264 times the mass of the electron. And we're asked to use this to estimate this range. Okay, so what we need to do is, well, let's get the uncertainty in E first. That's equal to mc squared, which is equal to 264 times the mass of the electron times c squared. Okay, now delta t, that's going to be greater than or equal to h bar on 2 over delta E, which is equal to h over 2 pi times 2 times delta E, which is 264 mec squared. So now we can just substitute in our numbers. We've got 6.626 times 10 to the minus 34 over 2 pi times 2 times 264 times the mass of the electron, which is 9.109 times 10 to the minus 31 times c squared, which is 3 times 10 to the 8 squared. So we can solve this on the calculator and we get that these virtual particles can be created for 2.436 times 10 to the minus 24 seconds without violating our uncertainty principle. So now to get how far they go, they travel a distance c delta t, and that's at most. And so we multiply this by 3 times 10 to the 8. And we get 7.3 times 10 to the minus 16 meters. We should probably just give it to one significant figure as there's lots of uncertainty here. So it can go 7 times 10 to the minus 16 meters, and so that's roughly the range of the strong nuclear force.